All right, so in this example right here, we're going to decide whether each of the equations below defines a one-to-one function, and if so, find the equation that defines the inverse. All right, so let's look at for g of x here, and we have the square root of x minus 3 is greater than or equal to 3 right here, right? So these are our restrictions. So starting at 3 and then and so forth. So if you know what the graph of this radical function looks like, it will look something like this here, starting at 3. 1, 2, 3, and it's going to look something like that right there, right? Another cool, powerful tool is that you could also use Desmos to do the same thing there. So if you ever wanted to use that, you can do that. Maybe like I could just show you here real quick what that would look like. And I'll just kind of put you in the viewing window here. So this is really neat because now like you can graph almost anything now and be able to have a dynamic graphing calculator. So square root, I'm just going to put SQRT x minus 3, and there we go. We have our graph ready there for us. So something that's really neat. You can zoom in and out. It's really neat, and you can kind of play back and forth with it. So like as we can see here, I mean, if you graph this, if you do a horizontal line anywhere on this thing, it's going to be 1-to-1. So we've kind of quantified that now, saying, well, yes, it is 1-to-1. So we know that's true. Now it says, if so, find the equation that defines the inverse. And what's really neat is that the inverse will always be a reflection of the line y equals x. And Desmos can also be really neat thing here. So let me first call this graph right here like f of x. I'm just going to give it that name, right? So now if I graph its inverse, let's see if this is going to work here. Let's see if I graph that, what will it do? Will it graph it for me? No, not quite required argument. Yeah, so I guess I can't just go and graph it right there. Oh, well, it's all right. But so basically, that's what we want to try to find right now. Is we want to be able to find this equation that when you graph the line y equals x. So if I just kind of put that in right now, something that looks something like this. If I have the line y equals x, okay, you should see a reflection of this graph right here. An exact reflection. So from here to there, see how it's exactly that many, that distance from the line y equals x. Well, in the same way, we should get something that looks something like this then. How it should be a mirror reflection. That like if this goes here, that goes there, and so forth. So that's what we're trying to find. We're trying to find the equation of what is this then right here. And if you kind of look at it, it kind of looks like we should have some kind of x squared, right? It kind of looks like a parabola right now. So let's see what happens here. And here we have the steps. If you're going to find a function, you do these. If you're going to find its inverse, you're going to do these 3 steps. You're going to first interchange x and y. Then we're going to solve for y, and then just replace y with f inverse of x. Okay, so let's go and do that then. All right, so g of x is a fancy way of just saying y. So I'm just going to rewrite that so we can see that right now. So step 1 says interchange x and y. So I'm just going to switch them. So x equals the square root of y minus 3. That's our first step right here. Okay? Bing! So we're done with that. Now let's solve for y. All right, so I'm going to first get rid of the square root. And so I'm going to square both sides. So now I get x squared equals y minus 3. And I'm going to go ahead and now add 3 to both sides. So now I'm left with x squared plus 3 equals y. Okay. Now something real important here that that we want to distinguish, that which you really can't quite see until you know what the graph kind of looks like right here, is notice that our graph starts at the x value of 0. And then it goes to x equals 1, 2, 3, and so forth. So really, we want our restrictions to be where x is greater than or equal to 0. Now, you you may be saying right now, but wait a minute though, man. Like, you just knew what the graph looked like. I mean, like, how are we supposed to know what to make the restrictions? Well, good question. So if you don't know what the graph looks like, if you graph this, right? So I'm just going to do a really rough sketch right now. If you graph this right now, and that's a really rough sketch, right? By the way, disclaimer, not drawing the scale. So we know that the graph looked like this, right? So if you have this using intuition, you're like, oh, wait a minute. Well, it can't be that guy right there. It can't be this part of the graph because that's not a reflection. A reflection of this would be something like this right here. So that's why we can just scratch all this off, because any inverse has to be a reflection across the line y equals x. That will always happen, right? So that's kind of how I knew, okay, well, I'm going to start at 0, and then it's going to go on for all these x values. So that's another way how you can figure that out. Okay, let's just do another one right here. And so first of all, is x cubed minus 4 1-to-1, right? And you may or may not know what this graph looks like. And this is a cubic graph. So we can even go to our Desmos over here, and we can do that. Let me just turn off the smart link thing. This thing kind of turn that off. So we can do g of x, and then x to the power 3. And what was that? Minus 4. Cool. So let's just go in and zoom out here so we can kind of see what the heck is going on here. That should be a power of 3. Cool beans. And there we have it right there. So like as we can see right now, this guy is going to be 1-to-1. You know, right here we have our point of inflection, but it still is not going to hit it more than once if you do a horizontal line test. So yes, of course, this is 1-to-1. Now can we find its inverse? So if we do the little steps again, the steps is to first interchange x and y. So we have x equals y to the power 3 minus 4. Second step now is solve for y. So I'm going to add 4. So x plus 4 equals y cubed. And then I'm going to get rid of the cube, which means I'm going to take the cube roots. So then I'm left with the cube root of x plus 4 equals y. So let's just kind of see what that looks like here. The cube root of x plus 4 equals y here. So I'm just going to kind of call this, I don't know, L of x. This is not what we call it here. And let's just do that there. And I'm just going to go like this. And our function was x plus 4 inside. I'm just going to raise this to the power of 1/3, which is just another way of doing the cube root. And so if we take a look at that, and I'm going to get rid of this guy right now. So that looks pretty interesting. And I'm wondering, can you visually see how that's a reflection across the line y equals x? And if you can't, then let's just draw it in there. Y equals x. And as you can see now, you know, this point is reflected across the line y equals x. That point is reflected across. It's like a mirror image of each other across the line y equals x. So this is a test right here. You could always test and see if it is by also using this, you know, great resource, Desmos, to see whether or not they really are inverses of each other or not. And that would be it right there then.